Okay. Good morning, everybody. Thanks for coming. We've had 6 lectures so far.
Sorry to interrupt, sir, but YouTube link.
YouTube link is exactly well, I mean, it's on my channel, but I'll share it anyway. I'm sure eventually you'll figure that out. But, okay. All right.
Thank you, sir.
Now, so far we have talked about, we started talking about the principle of relativity and one experiment which was designed to test, which was indirectly a test of this principle. And, that is not how the experiment was designed. It was, because they didn't really think about the principle of relativity. It had not been formulated in this way until Einstein then came along. But effectively, this experiment served as a test of the relativity principle. So, and this experiment gave a null result. So null result means that there were some interference fringes which were expected, but some changes in the interference fringes which were expected, but those changes were not observed. So the velocity of the Earth in the solar system was in its motion around the sun is not detectable by observers on the Earth. So that is the bottom line. That is the statement. That is the result of the Mitchelson-Morley experiment. So lecture 7. 29. Okay. So what is the second notification? So what is the Michelson-Morley failed to measure the velocity of the Earth in its motion around the sun, right? So this is a test of the relativity principle, right? Because basically it says that if you are in your own frame of reference, you cannot measure your own velocity with respect to some other frame of reference, right? You can measure the velocity of some other observer moving in some other frame of reference relative to you, right? But there is no way in which you have an absolute velocity of your own which you can measure, right? Now, so this confirms the relativity principle, right? Which I've already mentioned to you what the relativity principle is. That the laws of physics are the same for all inertial observers. So this is the way that Einstein stated this principle. So now, to account for the fact that in the Michelson-Morley experiment, no change in the fringes was observed, Fitzgerald and Lorentz, they proposed this contraction hypothesis. They said that, well, for some reason, something to do with the electromagnetic fields and the interactions between electromagnetic fields and atoms and whatever the structure of matter, when an object moves, it undergoes a contraction in its length in the direction of motion. And that contraction is given by a certain factor. And if you put this factor into the Michelson-Morley experiment, then what you find is that because of this contraction, whichever arm of the Michelson-Morley apparatus is moving in the direction, is aligned with the direction of motion of the Earth, that arm will shrink by just the right amount. And because of that shrinking, the time it takes for the beam to travel up and down and left to right will be the same. So there will be no observable change in the phase, relative phase of those two beams. And if there is no relative change in the phase of those two beams, then you cannot detect this velocity u, right? So then this question, right? So this explains the principle of relativity. Now, are there any questions about this at this point? Okay. If you have any questions, you can always just unmute yourself and ask the question. Okay. Now, right. So there is another thing that the Michelson-Morley experiment was trying to do, which is that it was trying to detect the presence of something called the ether, also spelled as, or actually as spelled as in this way, with an A at the beginning, ether. So what is ether? Any of you know what ether is in common usage?
So I guess it was proposed as the absolute state of
all of that. I'm talking in like daily usage around the house.
Vehicle, electric
Huh?
vehicles, electric vehicle.
Electric vehicle? No, that is Tesla.
There's some
Or
sort
like
of
space.
aroma or something like that.
Aroma. Okay, go to your clothes. Aroma.
Scent, sir.
Okay. Huh?
Scent.
So nail polish.
Scent. Nail polish. Excellent.
Nail polish.
Now that is closer.
Excellent
Now,
solvent
this,
for
this
Nail
is
polish remover, sir.
The rain polish
Nail polish
remover.
remover. Excellent. Excellent. But
So
that's
it is
enough. Shant.
excellent solvent for extraction.
Beta, now I know the next step is to give me the chemical structure. I don't need that.
Oxygen connected to two alkyl carbon.
Okay, I get it. Okay. So what is ether? Ether is a synonym for alcohol, right? And alcohol in the sense, not in the sense of drinking alcohol, but medicinal alcohol, or like for the use of nail polish remover or something, right? And what is the property of this of ether, right? Is that it evaporates and it disappears very quickly if you leave it unopened, right? So this is also the source. This is also there is an expression called ethereal. Ethereal means something that is very hard to keep track of, something that vanishes. For example, you might say that so and so, her beauty was ethereal or something like that, right? I mean, if you want to get friend zone. So ethereal means something that is very hard to keep track of. Something that is invisible, vanishing. Okay. So now what does this have to do with physics? So you know that you remember that we said that that light or electromagnetic fields, they obey this equation, which is called the wave equation. Right? And so this means that, well, light is a wave. Okay. Now, the thing with waves is, when you think about waves, where do you have waves? Give me some examples of waves.
Sound wave,
Sound waves.
ripples,
Huh?
ripples,
Water
ripples.
waves,
Water waves.
Radio wave.
Radio waves, but that comes under light. Okay, so we'll what else? Okay, radio waves, fine. Then you can have waves in objects, right? Mechanical vibrations,
longitudinal.
right? Different. Those are different kinds. You can have mechanical vibrations, right? Then you can have the Mexican wave. You know what the Mexican wave is?
Yes, sir.
Right? Everybody knows what the Mexican wave is. No?
No, sir.
No, sir.
No, sir.
It's what you do in stadiums when everybody raises their hands like this and then lowers them.
Oh,
Then the next person next to you raises their hand, and the next person raises their hand. So when everybody does that, you get a wave which moves. Right?
why it is called Mexican, sir?
Well, I don't know. I have no idea. Maybe because somebody in Mexico did it first. So
Yes, sir.
I mean, I don't know. So so what is the common aspect of all of these? What is the common aspect of sound waves, water waves, mechanical vibrations, and the Mexican wave?
Propagation.
They
Huh?
need a medium. They need a medium.
तुम लोगों ने पढ़ के आए हो ना? So you need a medium, right? You need some substance through which the wave propagates. Right? So what is the medium for the case of sound? It's just air molecules.
Air molecules.
Yes.
So for sound, you have air or some gas in general. All right. For water or for fluid
Water
waves in
molecule.
general, you have some fluid. For mechanical vibrations, you have a lattice. Right? So in a mechanical substance, you have a lattice of atoms, and that lattice vibrates. And then in this Mexican wave,
And
you have people, right? People are doing something. So in all of these cases, you have a medium, right? And elements of that medium are oscillating, and those oscillations combine to give you a wave. Another kind of wave, which I forgot, I mean, it's related to these, but you can think of it, is in a string, right? So one-dimensional waves in a string, for example. Now, this this wave, right? So people ask the question for light, right? What is the medium?
No medium, vacuum.
This is the wave, this is the medium, right? So it's a vacuum, right? So vacuum is empty. So I mean, but that doesn't make sense, right? I mean, from the understanding of physics,
Particle.
we need to have some sort of medium, right? So maybe the vacuum is not empty, right? This is the idea. The vacuum is not empty. It is filled with something. But it is
Energy.
filled with some. I'll tell you, when I tell you, you can. It is filled with something, but that something, you cannot touch it, you cannot see it, you cannot conduct any experiments really. I mean, it's not visible. You cannot do any optical experiments to test for the presence of this material, or mechanical experiments, right? So what is it? It's filled with this something like some ghostly substance, right? So this substance was therefore was referred to as the ether. Okay, so it's some substance. So we don't know what substance it is, but this was the idea, that the vacuum is not empty; it's filled with some substance, and that substance is ethereal, right? Which means you cannot sense its presence. It is very difficult to observe in any way, right? So the Michelson-Morley experiment was an attempt to search for this ether. Was right? And now you cannot observe this ether directly. So what is the point? The point is that you're trying to measure the velocity of the Earth. But with respect to what? With respect to the ether. Right? So you have some background, some medium in the back, in which everything is moving. And so the idea is that you're trying to measure the velocity of the Earth. With respect to this ether, right? So when the Michelson-Morley experiment gave a null result, people tried to come up with all sorts of explanations. And they thought, well, maybe the ether is moving in such a way, right? There could be some drift of the ether might have a drift also. And maybe the ether moves in such a way that, you know, it changes the length in just the right way. Or if you take into account the motion of the ether, then you won't get any results. But the problem is that this experiment is conducted at different times of the year, where the Earth is in different locations. And every time you are getting a null result, right? So the ether's motion has to be very, very complicated. Right? The ether's motion has to be perfectly aligned with the motion of the Earth for some reason, right? To give you a null result every time. So this becomes a very complicated picture, because you have to postulate a medium, then you have to say what are the mechanical properties of the medium, what are the optical properties. Then you have to say that the medium, for some reason, its motion is synchronized with the motion of the Earth. Right? So what Einstein, he asked this question, right? Is the ether needed? Like, I mean, let's say you throw away the ether, right? And instead, it doesn't, so throwing away the ether doesn't solve this original question of what is the medium, okay? That question, it still persists even to this day. So now we have a different understanding of this ether, this vacuum, okay? We have a different understanding of space-time as a medium. But it's a medium in which things move such that the laws of special relativity are obeyed. So you cannot detect any motion with respect to this ether. But that kind of knowledge and that understanding and technology was not present in Einstein's time. So Einstein did the best he could, right? Einstein said, well, what are the minimum number of assumptions I need to explain the present status of theoretical physics? So the first assumption he made was the principle of relativity, which is the statement that all the laws are same for all inertial observers. And what is an inertial observer? An inertial observer is a non-accelerating observer. Okay. Now you might object at this point and you might say, well, the Earth is not an non-accelerating, it's an accelerating frame, right? It's rotating. So relativity should not apply. But if you look at the Earth in over a small duration of time, as it moves in its orbit, right? During that small duration of time, the Earth there is an acceleration, but it's very small. For all purposes, right? For the purposes of the experiment, because the experiment is being conducted on a certain time scale, how much time it takes for the light to go up and down, for instance. That happens very quickly, right? Nanoseconds or picoseconds or femtoseconds. In that amount of time, the Earth, it accelerates very, very little, right? Its velocity changes by a very, very small amount, negligible amount. So the Earth is also an inertial observer for the purposes of this Michelson-Morley experiment. The second assumption that Einstein made was that the speed of light is the same in all frames of reference. Okay. So now, I mean, one might argue that if you have the first postulate, you don't really need the second postulate, because if the laws of physics are the same for all observers, inertial observers, then one of the laws of physics is the Maxwell wave equation. And this equation tells us that light moves at some speed c. Right. So if this law is the same for all observers, right, this implies that c is the same for all observers. Okay. So one of the exercises I gave you in a couple of lectures ago was that I asked you to check the Galilean properties of this equation. That means if you go to a frame of reference that is moving with respect to these coordinates, x and t are some coordinates, right? This is some frame of reference. So you go to a different frame of reference. So what happens according to the Galilean transformation, the coordinate transforms in this way, and the time at most it can change by some constant amount, right? This is some constant. My writing is becoming very bad because I've been writing since 8 o'clock this morning. This is the first class. So if you look at the Galilean invariance of this equation, invariance means whether or not something changes. So in the exercise, I told you that, well, you should write down d by dx in terms of x prime and dt prime. So how do you do that? This is the chain rule. And the chain rule applied for derivative operators. So remember that if you have some function f of x prime, and x prime itself is a function of x, let's say, right? Then how would you calculate df by well, how would you calculate just df? Right? What would you say? You would say that what am I? So you would say that, right, df by dx, let's say you have to calculate df by dx. What is df by dx? It's df by dx prime by dx, right? Now this expression I can write in this way: dx prime by dx and df by dx prime, putting the function at the end. So if you look at this expression, I can write the expression like this: d by dx of f. This expression I'm writing as d by dx of f is equal to dx prime by dx, d by dx prime of f. Right? This expression and this expression is the same thing. But now what I have done is I have separated the operator. This is an operator, right? These are operators, and this is true for all functions f, right? This applies for any function as long as that function is differentiable. So that means d by dx, the operator d by dx, can be written as dx, right? And this is for a function of one variable. Sorry, I just muted somebody because there was some background noise. But if you want to ask a question or you want to say something, please mute yourself. Okay. Now, what if I have a function of two variables, like x prime is a function of x and t? Then what do we say? We say that df by dx. Now I can calculate the derivative of f with respect to x and with respect to t. So in this case here, these should all be total derivatives actually. Df by dx is equal to df by dx prime by dx. Okay, so total derivatives rather than partial derivatives. But here I have to calculate partial derivatives because f depends on two functions x and t. So what is df by dx? Df by dx would be df by dx prime by dx. This is one term, right? But x prime, so once again, Right. D by dx. Right. So sorry. D by dx is right. So this is fine. Dx prime by dx, df by dx prime. And okay, let me write this. F is a function of x prime and it's a function of t prime. And x prime and t prime are both functions of x. So then I will get two terms here. D of x prime by dx and d of t prime by dx. And then df by dt prime, like this. Right? So if you compare these two expressions, if you look at this expression and this expression, right? This expression is just the operator version of this guy, right? Again, I'm putting the function outside, and since it is true for all functions, that means the operator d by dx is equal to dx prime by dx times d by dx prime plus dt prime by dx times d by dt. Okay.
Sir,
Yeah. Yeah. Somebody said something, sir. Then you didn't
sir,
follow up.
sir, myself that
Ah,
I was I have not unmuted myself. So can you explain that function and its partial derivative once again? That I had a confusion that df by dx equal to uh, dx dash by dx into something.
right.
So after
So,
cancelling that dx prime
so
and dx prime and dt prime and dt prime, we get df
we're
by
not canceling anything. No, you can't cancel this, right? You can't do something like this. You can't do any cancellation like this. Is that what you're talking about?
yeah.
No, you can't do that, no?
Why? But that are the identical terms.
No. So this is dx prime by dx itself is a function, no?
Yeah. Sorry, sir.
And then d by dx prime is an operator.
Yeah.
So I'll give you an example. Let's look at something like this. Okay, let's look at some function of x and y. Okay, let's say fxy is equal to x square plus y square, or rather, let me write it as xy. Now let's say that you change your coordinates. Let's say you go from Cartesian coordinates to polar coordinates, right? So then in polar coordinates, you have r is equal to root of x square plus y square, and you have the angle phi. Phi is equal to tan inverse y by x. You have all seen this before.
Yes.
Yes.
So f is a function of x, but x is a function of r phi, and y is a function of r phi, right? And what is it? X is equal to r cosine phi, and y is equal to r sine phi, right? So now if I want to write down the derivative of f with respect to r, right? df by dr, right? How would I do that? Well, I would take the derivative of f with respect to x. Then I would multiply that by the derivative of x with respect to r, right? This is the chain rule. But f depends on two variables, x and y. So the chain rule has two terms, I have to put a second term also, dy by dr, right? This you know, right? This first part.
Yes, sir.
Maybe what you're unfamiliar with is this what happens with more than one derivative. Maybe this is what you have not seen before. So this is the chain rule, but for multiple variables. Okay, so I'm not going to give a proof of this. You can find a proof online on Wikipedia or something. Just a chain rule for multivariable functions. So then again, I'm writing this as d by dr of f is equal to dx by dr, d by dx plus dy by dr, d by dy, whole thing at 1x, right? It's exactly the same expression. But now you see, right, that I cannot do any cancellation like this. This is not allowed, right? I'm not doing any kind of I'm not doing an integral, right? If I was doing an integration, then maybe I could, do that. But here I can't do that. So it's exactly the same thing. Instead of r and phi, I have x prime and t prime, right? So I have x and t that goes to x prime and t prime. So d by dx is equal to dx prime by dx, d by dx prime, dt prime by dx, d by dt. Does this make more sense to you now?
Yes, sir.
Hopefully it does. I don't know if you have to sit down and work this out for yourself, right? So I'll give you another exercise for this purpose, right? Which is that work out the form of d by dr and d by d phi in terms of, so you can just write dou x, that means dou by dou x. This is just a shorthand notation, okay? Now this is easy. This is just the first part. The second part is a little bit more. The second part is work out the second derivative, d square by dr square and d square by d phi square. So to work out these expressions, you have to apply this chain rule twice, right? You have to find d by dx squared, let's say, you would apply this thing twice. So this is what needs to be done in this, when you look at this wave equation. So when you look at this wave equation in these new coordinates, what will happen is the wave equation no longer has the same form. You will get d2 squared by dx prime squared, 1 by c squared de squared by dt prime squared. Then you will get some term. You will get a term which involves d2e by dx prime dt prime. You'll get a mixed term. So the wave equation is not preserved under Galilean transformation. Okay. So the question then is, under what sort of right? So the Galilean transformation is not the correct transformation, right? So what should be the correct coordinate transformation That means I have some observer, x prime, p prime, and some observer xt, let's say O and O prime, right? And what we are saying is that if this observer is moving with some speed, let's say v naught, then this is the Galilean transformation, right? So we are saying this transformation is not correct anymore. There is some other transformation, that means there is some other function of x and t, right? What should be the form of this function f? And in the Galilean case, you also have this transformation for the time, but this whole thing is incorrect, right? So the question is that what are these two functions f and g, such that when you go to the new coordinate system and you write down d by d x prime squared, and when you write down d by dt t prime squared, the wave equation remains exactly the same. So after going to these new coordinates, the wave equation remains invariant. What should be the form of these functions? And the answer is that this f and g are given by what we call the Lorentz transformation. Okay. So what is I'll just write down the form of the Lorentz transformation today. Right. Now the thing is that so this is the Lorentz transformation. So what it is saying is that, right, if you want to go from one frame of reference to another frame of reference, how should you translate the coordinates? The coordinates should be translated according to this dictionary. Okay. And this, when you do it according to this dictionary, what will happen? You remember we derived the velocity addition law. How did we derive it? We derived it from the Galilean transformation, right? We took the Galilean transformation and we took the time derivative of the Galilean transformation, right? So we took x prime is equal to x minus v naught t. We took the time derivative of both sides. That means v prime is equal to v minus v naught, right? This is the velocity addition or subtraction or whatever you want to call it. Now, when you derive velocity addition from this expression, what will happen is your velocity addition formula will be changed. Okay, and we will look at the derivation. So when you have this, what you will get is something like this: v minus v naught over 1 minus v times v naught by c square. So this is also velocity addition, but now this is the velocity addition according to such that the postulates of Einstein What are the postulates of Einstein? The first postulate is the relativity principle. The second postulate is that the speed of light is the same in all frames of reference, right? Now imagine that you have these two frames of reference, right? And so this is your O prime and this is O. And in O's frame of reference, there is somebody holding a torch. And that torch emits a beam of light. What is the velocity of this beam of light as seen by O prime? It's c. Now O prime is moving with respect to O at some speed v naught, right? So what is the speed of this wave as seen by O? So according to O, if you use the Galilean transformation, what is the speed of that wave as seen by O? So let me call this C prime. It is C is equal to C prime minus V naught.
V naught T.
Right? This is the velocity of the object or the wave in this frame of reference. So as seen by this observer, the same object or wave has a velocity C prime minus V naught, right? But what if I use the relativistic formula? If I use the relativistic formula, according to the Lorentz transformation, what is this C? C is equal to C naught minus C prime minus V naught over 1 minus V naught C prime by C square. Okay. But now remember that this is a beam of light. So for light, since this is a beam of light, this means that C prime is equal to, I'll write it as C naught square. Okay. This speed of light I'll write as C naught. So C prime is equal to C naught. Okay. So for light, so what happens? What do you get for the velocity c? You get c naught minus v naught, 1 minus v naught c naught by c naught square. Cancel c naught, you get c naught. So the speed of this beam of light as seen by this other observer is also c naught. The speed of this beam of light as seen by the first observer is c naught, as seen by the other observer is c naught. You can ask what happens if this observer is moving in the opposite direction. If it's moving in the opposite direction, for opposite v naught, you will get c naught plus v naught, 1 plus v naught c naught by c squared, or c naught squared, which will be equal to c. But if you use the Galilean transformation, you would have to add the velocity of the moving thing. Right? So this transformation, this Lorentz transformation, satisfies the two postulates that Einstein, postulated. The first is that the laws of physics are the same in all frames of reference. So which means what laws? The laws of electromagnetism. Maxwell's equations remain the same for the moving observer and also for the stationary observer. But more importantly, there is no such thing as a moving observer or a stationary observer, because all motion is relative, right? This also leads, this Lorentz transformation leads to Lorentz contraction, length contraction. It also leads to another result, which is called time dilation. And it leads to something else, which leads to the mass energy formula. That's the most famous result of relativity. And it also, well, it gives us a lot of other things. So this is the now in the next lecture, tomorrow's class, I will derive this Lorentz transformation. Okay, you can actually derive this expression. I will derive this expression, and then yeah, and then we will look at things like length contraction, and we'll also look at something very nice, which is called space-time diagram. Now, this space-time diagram picture is not in your syllabus. It's not an official part of the syllabus, but it is a very powerful way of understanding relativity. And then we will look at something called space-time intervals. And so somebody asked me a question in the chat about that today. So we'll be talking about things like space-like and time-like and all that. Okay, so I'll stop here. And I know my classes run a little bit long, but I hope you all don't mind that, right? Okay, so class is over. You can leave. If you have questions, you can ask them. Questions?
Sir, I didn't understand perfectly why Galilean expression was wrong, sir.
Well, it's wrong because it's wrong. I mean, because this equation is not, the form of this equation is not preserved under Galilean transformation, right? That's why I've given you that exercise, right? And I've given it to you again today in a slightly different form in terms of this R and phi, to sort of so that you can do a little bit of warm up. So if you can calculate this R phi square, this will also become very important later when we look at electromagnetism. So this this requires you to sit down and do a little bit of algebra, okay, which can be annoying, I know, but well, that's life, I guess. Okay.
Yes, sir.
Any other questions? No. Okay, I'll stop the recording and the live streaming.